You're looking at a stellar nursery, young stars only a few million years old, captured in this stunning image by the James Webb Telescope. In a stunning breakthrough that has electrified the scientific community, the James Webb Space Telescope, JWST, has reportedly detected an astonishing 750 galaxies beyond the traditionally defined bounds of the observable universe. These findings are not just an extraordinary testament to the capabilities of the JWST, they challenge the very framework by which humanity has understood cosmic boundaries for decades. Physicists estimate that the universe began approximately 13.7 billion years ago with an event known as the Big Bang, a moment of incomprehensible intensity that gave rise to all matter, energy, space, and time. Despite the widespread acceptance of the Big Bang as the foundational theory of modern cosmology, the actual cause or trigger behind this event remains one of the deepest unsolved mysteries in science. Over the past century, cosmologists have developed detailed models describing the universe's evolution from its earliest moments, relying heavily on a combination of theoretical physics and observational data. A key component of these models involves dark energy, a mysterious force believed to be more dominant than all visible matter in the cosmos. This energy is thought to drive the accelerated expansion of the universe, a process that has continued since the Big Bang. Yet, as our tools for observing the universe have advanced, especially with the launch of the James Webb Space Telescope, JWST, the data emerging from deep space has begun to challenge long-held assumptions and compel scientists to re-examine the very framework upon which our understanding of the universe rests. One of the most profound disruptions to the established model comes from JWST's discovery of over 750 new galaxies, some of which appear astonishingly different from what cosmologists had predicted. These galaxies, observed at immense distances, are believed to date from just a few hundred million years after the Big Bang. What has stunned the scientific community is not just their quantity but their unexpected maturity. Instead of chaotic, irregular shapes, the kind predicted by standard models of early galaxy formation, JWST has revealed galaxies that are smooth, compact, and disk-like, with structures similar to modern galaxies. These findings are difficult to reconcile with a traditional Big Bang model, which asserts that galaxies formed hierarchically through small-scale mergers and interactions over billions of years. In the standard scenario, galaxies began as clumps of matter that gradually coalesced into larger systems via violent collisions. The idea that well-formed, organized galaxies could exist so early in the universe's history runs counter to this narrative and has triggered what some scientists have called a panic moment in cosmology. Another startling revelation from JWST is the apparent size and density of these ancient galaxies. Contrary to the expectations set by the expanding universe model, which predicts that early galaxies should appear larger due to their position in a denser, younger cosmos, the galaxies seen by JWST are smaller and more tightly clustered than anticipated. This challenges interpretations of cosmic redshift, the phenomenon by which light from distant objects is stretched to longer, redder wavelengths as space itself expands. Redshift has long been used to estimate distances and ages of celestial bodies, providing crucial support for the Big Bang model. However, if galaxies from the early universe appear smaller and more structured than predicted, it may suggest that our understanding of redshift, and perhaps the expansion of the universe itself, needs revision. The smoothness of these galaxies also raises important questions. In the turbulent early universe, astronomers expected galaxies to be uneven and distorted, shaped by frequent interactions and high-energy processes. Yet the galaxies seen by JWST exhibit none of this expected irregularity. Their smooth and mature appearance implies either that galaxy formation occurred much faster than previously thought, or that our entire model of galactic evolution needs to be revisited. The hierarchical merger scenario, long a pillar of cosmology, may not be the primary process by which galaxies formed. Instead, galaxies might have developed through more efficient or entirely unknown mechanisms operating in the first few hundred million years of cosmic history. These findings have prompted some scientists to question the fundamental assumptions of cosmic inflation as well. Inflation theory posits that the universe underwent a brief but exponentially rapid expansion immediately after the Big Bang, smoothing out irregularities and setting the stage for the formation of galaxies. This process was thought to account for the uniformity of the cosmic microwave background and the large-scale structure of the universe. However, if galaxies formed earlier and in more significant numbers than inflation theory allows, it may suggest that inflation occurred differently, or not at all, in the way we currently understand it. Adding to the complexity, JWST's observations also show unexpected clustering of galaxies in the early universe. According to the Big Bang model, as the universe expands, galaxies should become increasingly dispersed. Yet what JWST reveals is the opposite: tight clusters of galaxies in regions where they should be more sparse. This denser-than-expected distribution implies that either matter was arranged differently at the universe's inception, or that forces beyond gravity, perhaps modifications to general relativity or entirely new cosmic interactions, were at play. Such anomalies are leading some researchers to explore alternate cosmological models, including theories involving a variable speed of light or radical reconceptualizations of space and time. Even more fundamentally, the JWST data casts doubt on the accuracy of redshift as a reliable metric. If galaxies observed at extreme distances already appear ancient and structured, then either they formed much earlier than the Big Bang model allows, or our interpretations of redshift are flawed. This problem touches the very core of modern cosmology, which relies on redshift not only for dating celestial objects but also for estimating the scale and expansion rate of the universe itself. Some scientists have begun to entertain the idea that redshift could be influenced by unknown factors, perhaps environmental conditions near galaxies or interactions with dark energy and dark matter that distort light in ways not accounted for by current models. This has also led to renewed scrutiny of dark matter and dark energy, two components thought to constitute about 95% of the universe's total mass energy content. If galaxy formation and clustering occur in ways that defy predictions based on these entities, then our understanding of their nature and role in cosmic evolution may be incomplete. Dark matter is believed to provide the gravitational scaffolding necessary for galaxy formation, while dark energy is thought to drive cosmic acceleration. Yet if observations do not align with the effects expected from these forces, it could mean that their properties are more complex, or altogether different, than previously assumed. The implications of JWST's findings are monumental. If further observations continue to confirm that the early universe was filled with numerous, small, well-formed galaxies, then the current cosmological framework may need to be overhauled. This doesn't necessarily mean the Big Bang never happened, but it could indicate that our model of what occurred after the initial expansion is far too simplistic. It may require scientists to formulate new theories of galaxy formation, revise their understanding of cosmic inflation, or even propose entirely new cosmological models to account for the discrepancies. The James Webb Space Telescope has effectively opened a new chapter in our exploration of the cosmos. It has provided an unprecedented glimpse into the universe's earliest epochs and revealed a reality far more complex and enigmatic than previously imagined. Rather than confirming our theories, JWST has raised more questions than it has answered. The discovery of smooth, mature galaxies in the early universe poses serious challenges to our understanding of space, time, and the forces that shape them. It suggests that the universe may have evolved through processes still unknown to science and that our cosmic origins are wrapped in deeper mysteries than the Big Bang theory can currently explain. As new data continues to arrive, scientists must grapple with the possibility that they are witnessing the beginning of a cosmological revolution, one that could redefine humanity's place in the universe. The revelations from the James Webb Space Telescope, JWST, are not just minor adjustments to existing theories. They may represent a paradigm shift in our understanding of the cosmos. For decades, the Big Bang theory has served as the dominant explanation for the origin and evolution of the universe. It has explained the cosmic microwave background radiation, the abundance of light elements, and the expansion of space itself. But now, as JWST peers deeper into the early universe than ever before, it is uncovering evidence that appears inconsistent with the expected sequence of cosmic events. The fundamental assumption of the Big Bang theory is that the universe began as a singularity, an infinitely dense and hot point where all matter and energy were compressed. As space began to expand, the universe cooled, allowing for the formation of subatomic particles, then atoms, and eventually stars and galaxies. According to this timeline, it should have taken hundreds of millions, even billions, of years for galaxies to mature into well-organized spiral or disk-like structures. The JWST, however, has revealed that such galaxies already existed just a few 100 million years after the Big Bang. This suggests that complex galactic structures formed far more quickly than our models permit, or perhaps that the starting conditions of the universe were dramatically different than we thought. Another profound implication of the JWST data involves the distribution and density of galaxies in the early universe. The Big Bang model predicts a relatively uniform expansion, leading to a gradual thinning out of galaxies over time. Instead, JWST reveals clusters of galaxies that are tightly packed with more mature features than they should possess at their observed age. This contradicts the cosmological principle, the idea that the universe is homogeneous and isotropic on large scales, and introduces uncertainty into the standard model. If early galaxies were already grouped in clusters, it implies that gravitational interactions occurred more rapidly, or that some unknown mechanism was accelerating the process of galactic organization. This also brings into question the nature of gravity and its role in the early universe. General relativity, Einstein's theory of gravity, has been a cornerstone of cosmology for over a century. It explains how matter shapes the geometry of space and how that curvature affects the motion of objects. But general relativity alone cannot explain all the features of galaxy formation, hence the need to invoke dark matter, an invisible substance that adds gravitational influence without emitting light. If JWST's observations cannot be reconciled with predictions based on dark matter and general relativity, then new physics may be required. This could mean modifications to gravity itself or the discovery of new forces that act over cosmic distances. Furthermore, the nature of cosmic redshift, one of the primary pieces of evidence for the universe's expansion, is now under renewed scrutiny. Traditionally, redshift is interpreted as a Doppler-like effect. Light from distant galaxies is stretched as the space between us and them expands. This is a cornerstone of the Big Bang model and the primary reason we believe the universe is growing. However, if galaxies are appearing older, smaller, and more mature than expected, it raises the possibility that redshift could have other contributing factors. Alternative explanations have been proposed over the years, such as tired light theories or variable light speed, but these have largely been dismissed due to lack of evidence. With JWST's findings, however, these ideas may warrant a second look. It is also worth considering the role of time itself in these cosmological models. Our current understanding assumes a linear progression from the Big Bang to the present. But what if time behaved differently in the early universe? Some physicists have proposed that time may not be a fundamental constant, but rather an emergent property of a deeper quantum framework. If true, then the timeline of galaxy formation and cosmic expansion could be distorted in ways we cannot yet comprehend. The existence of mature galaxies so early in cosmic history could thus be a sign that our concept of time on universal scales is incomplete or flawed. In light of all these challenges, some researchers are now exploring radical alternatives to the Big Bang theory. One such idea is the bounce model, which suggests that the universe undergoes cycles of contraction and expansion with no true beginning or end. Another is the emergent universe model, in which the universe slowly evolved from a static or quasi-static state before beginning to expand. These models aim to address some of the shortcomings of the Big Bang theory, such as the singularity problem and the inflation puzzle, by offering different explanations for the observed structure of the cosmos. The tension between theory and observation has long been a driver of scientific progress, and we are now at such a crossroads in cosmology. Just as Copernicus challenged the geocentric model and Einstein upended Newtonian mechanics, JWST is providing evidence that may force a dramatic rethinking of the universe's origin story. Scientists must now develop new models or revise existing ones to account for early galaxy maturity, clustering, and structural smoothness. Of course, this doesn't mean that everything about the Big Bang theory will be discarded. Much of it remains supported by a wealth of evidence, from the cosmic microwave background radiation to the observed abundance of hydrogen and helium. But cosmological models are intricate, and they must evolve to incorporate new data. It may be that we keep the broad framework of the Big Bang while modifying our understanding of what happened in the first billion years. Alternatively, we might replace the entire model with something more comprehensive, just as Newtonian gravity was superseded by general relativity, even though Newton's equations still work for most practical applications. One of the most exciting aspects of this scientific upheaval is the promise of new discoveries. As JWST continues to observe the universe, it will collect more data on galaxies, nebulae, black holes, and potentially even exoplanets. Each image could offer new clues about the early universe, providing both confirmations and contradictions. Scientists are now using sophisticated simulations and machine learning algorithms to analyze JWST's data, hoping to detect patterns that might reveal hidden laws of nature or point